that when you actually studied your mathematical physics, or you studied your let's say quantum mechanics, you have a lot of derivations and all. I think it's not humanly possible to cover all these topics in nuclear physics lecture. So it is considered that you have grabbed some concept from your previous lectures on quantum and mathematical physics, and you are moving ahead, because they everything goes hand in hand. So let me just tell you what are the important things that you should know actually from mathematical physics. The first thing is I think we already have seen yesterday, okay, that we were talking about those spherical harmonics, okay. So spherical harmonics, I think you should revise, okay, important, and check. And then one more thing that you should know is something which is called the Bessel function. Bessel function is also a part of mathematical physics, okay, very important. So Bessel function is there, okay, another one. And the third thing that you should know actually nothing but the Legendre polynomial. So Legendre polynomial also you have done. So these are all done in mathematical physics, okay. So you will see that these are nothing but their application, okay. So it's important that you actually apply these technology or the mathematical tools, okay. From quantum mechanics, I think most important would be the Schrodinger equation, okay, and I think this is more related to, and then you can easily understand this. So we will start with nuclear scattering. And nucleon scattering, what exactly do I mean by nuclear scattering here? We already have discussed a lot of things on scattering in the first unit, and that I think was important and very basic. We are going to go a step ahead now, and we are going to analyze it using the mathematical tool. All these, okay, all these. So what happens is, if you remember in the first unit, I said that whenever you have a target, okay, and then you basically have a wave coming in and hitting the target. It depends on what kind of target it is, what kind of input it is, okay. But in general, the wave function that you have, considering quantum mechanics and everything into picture, we basically have the wave function divided into two parts. So we have got two parts here, and if you remember, if the first part is nothing but the plane wave, so the first part will have the plane wave, okay, and so this is your plane wave, and the second part would be nothing but the spherical waves. Now why plane and why spherical? So if you remember again that if the incident is at a very high velocity, so this is basically called high energy scattering. So whenever we are considering nucleon and we are going to analyze a nucleon system, we are more or less considering a high energy scattering. So if you consider high energy scattering, that means the interaction time that this incident beam or the projectile we say have with the nuclei will be less. So the deflection will be minimum, okay. As a result of which this plane wave factor will be more or less valid. But if you consider a slower energy scattering, this interaction will be more, and it will basically get scattered in all different directions, okay, in theta, phi direction and so on. And then as a result, we also should need to consider spherical waves. So for simplicity, we most of the time do a plane wave. So if you just consider a plane wave, we are going to consider this e to the power ikz function. You say write down ikx, ikz and so on. So we can just take this function, okay. So we are going to analyze this particular function. We are going to see that how does it behave under different condition, okay. And then we will see that if we actually do the analysis, basically it is called the partial wave analysis. We're talking about a plane wave here. We are not analyzing the entire wave. So basically talking about a partial wave analysis. So that is a part of your syllabus, okay, and basically forms one of the complicated parts of nuclear physics. But before that, nucleon scattering, what does it mean? It means that you have electron, proton, neutron come hitting the target, and that target is basically nothing but your nucleon. So it might happen that your nucleon has only one proton or one neutron. We will see that one neutron is not possible. We have one proton, or you can have a neutron-proton system, and it scatters. So for simplicity, what we do is we are going to take a very simple system like deuterium we've seen, and we are going to study that. Okay, so we have already done part of it, and we are just going to continue from there. Okay, so if you basically consider a scattering schemes, okay, so this might not be a question. I won't ask you scattering schemes, because if I say scattering schemes, it's a very broad question. But only in terms of nuclear physics right now, we are talking about a proton-proton scattering. So what exactly it means that you basically have a proton beam. You have a proton beam and coming and hitting the nuclei. And the nuclei is very simple. It has got just one proton. It has got just one proton, and this is also a proton beam. So if a proton beam is coming in and hitting the proton, basically what is happening is a proton-proton scattering. Whether this is a high energy scattering or low energy scattering, we will see. Okay, but high energy scattering is something which is carried out most of the times. And then of course neutron-proton scattering. So neutron can be there, and then it will come and hit the proton. So there is a difference in analysis and understanding of proton-proton scattering and neutron-proton scattering. So what happens is when we talk about a neutron-proton scattering, there is no Coulomb repulsion as such, and as a result, we need to have some kind of low energy scattering. But when it is proton-proton, and if you was to consider only plane wave, okay, try to understand this. If you have a proton-proton, and if you want to have only a plane wave, you want to actually negate that Coulomb effect. So if we have it very fast, what will happen is the deflection will be minimum, okay, and then we can actually have only the plane wave and then analyze it. So the difference is basically a factor of Coulomb repulsion. So whenever we have two protons, there is a Coulomb repulsion. Neutron proton, there is no such thing as electromagnetic interaction. So the analysis totally tends to be different, and that's why whenever you open your book, any nuclear physics book, the scattering chapter will basically have a lot of things: proton, proton, neutron, proton. Okay, then why there cannot be a possibility of neutron-neutron scattering? First of all, we can do it. It's not that it cannot be done, but the thing is, technically the issue comes in that a neutron, a single source of neutron as a target is not a possibility. Okay, it basically is not a bound state. A single neutron is not a bound state. Until and unless you have a bound state, you cannot study it. Okay, so under decay scheme, what happens is a neutron will decay to proton in few minutes. If you have a neutron, if you are extracting a neutron, you can do that, but then you will see that it slowly will decay into a proton. So basically, effectively, you are studying only a proton-proton or a neutron-proton scattering. You need to have the system stable for some time, so you can carry out the scattering experiment. Objective question: why neutron-neutron scattering is not possible? Okay, what is the difference between proton proton scattering and neutron proton scattering? Why neutron neutron scattering is not a possibility? 2 marks question. Okay, I think this is very simple. Yeah, but I think the idea is immense. Okay, the idea is immense. Based on this, we can actually build our idea on scattering. Very important. So if we basically consider nuclear nucleon scattering, as I said in the first slide, we can actually have a low energy scattering and a high energy scattering, and somehow high energy scattering becomes a bit easy for us because we don't need to consider the spherical function and so on. But we will see that in the analysis, whatever we are going to do from now, we are actually doing a bit of spherical wave analysis also. So we are just going to take this in general. So we are going to take this in general. Just a sec. क्लास में क्यों नहीं हो? अभी आया समझ से मैं बोला. हाँ हाँ. क्लास अटेंड कर रहा था अभी हॉस्टल से. अच्छा. बोलो. अभी कर रहे हो क्लास? अभी आया था क्लास करने. तो क्लास करो, ऑनलाइन ही करो. So Rahul is here. So he's doing an online class. Okay. So we have this. Okay. So what happens is we have a projectile target. Okay, and then we have got the kinetic energy. So this is very simple, but then the idea you have to absorb. Okay, so sometimes we do get confused that for me at least, when I was doing my BSc MSc, that how can I have a single atom or a single nucleon and study the scattering process? Okay, so what happens is usually when we are studying these things, we are generalizing the case. Okay, so what happens is we actually take the target, we actually will have a number of atoms. So it's not that I'm taking a single atom, we do have a number of atoms, but what happens is all of these atoms are similar. Okay, all of them are more or less the images of each other, because if you're considering a gold foil, as in case of Rutherford's experiment, you have all the gold atoms, right? So all these will actually scatter and more or less give you a similar behavior. So this is more or less probabilistic in nature. What you do is you are studying the behavior of the entire system, which is composed of a single set of atoms, okay, a single atom which are actually all having a similar behavior. So it's not that you are just going to have one scattered beam or two scattered beam or three scattered beam. No, we are having lakhs and thousands and millions of scattering, okay. More the number of scattering, more perfect will be our result. And then when we actually relate it with the theoretical idea, we will see that this more or less fits into the scheme. And that means whatever experiment we are doing has a theoretical background, okay, and then that is more or less accepted. So whenever you basically have a beam, also the projectile target, as I said, it's obviously not that broad, okay. There is something which is called spot size. I think this is something which you all know because we have studied about spot size and all in characterization technique. So we have a narrow region through which a number of protons or a number of neutrons is coming and hitting the target. But then it's important to understand that when we do the analysis, the approach has to be that, okay. The approach has to be that we basically take a single neutron coming and hitting the atom, and then we are going to study it. And we know that even if we take a large number of atoms and a thicker projectile target, the behavior is not going to change much. That is important. So this is just an ideal case, a simple diagram and an illustration. So we do have this, and then we have got this angle theta, and then the beam gets splitted, scattered, the projectile beam, and then basically what happens is it is getting detected by the detector. So when it reaches the detector and when it was actually started from the source, the projectile, there will be a difference in its speed, there will be a change in its energy, there will be a change in its angular momentum, okay. And if we consider everything together, we can find out the information about the nuclei, the charge distribution and all those factors. I think this is something which we already discussed. What are these detectors? I think we already know. Even if you consider an XRT system and detector, consider a PMT tube, photomultiplier tube and all these are coming under detectors. So what happens is scattering at different angles are studied. So if I just go back to this picture, it's not that I'm going to just have a detector here. Whatever waves are getting or particles are getting scattered at this particular angle will be getting detected here. And if we have more waves, okay, it's going to get detected here. So we can get detection here and then we can get it here. So it's very messy, okay. It's not that simple. It's not that you are going to have an equal number of distribution on all sides. You might have a very more number of deflected rays on this side, but this side you might have less number of deflected rays, okay. That is possible, okay. So this is going to be random, but then if we actually average it out, we are going to get a good statistical distribution. So this is nothing but scattering at different angles are studied, okay. So it's not just one angle, we are studying it at different angles. So if we basically consider scattering, what we do is we are going to look into it from a mathematical point of view, like what is cross section and how many particles should be incident, or what exactly do I mean by intensity of the beam. Everything is going to be mathematical. So before I proceed with the mathematical relation, let me just make sure that all of us are on the same page as far as terms are concerned, okay. The first term is time. So I think time is very important because if you are allowing a target to be hit by proton or neutron beam, for how long it is incident on the system, very important. For the longer period it is incident on the beam, on the system, you will basically have a good or a better result, okay. So that means time plays a very important role. Next is solid angle. So if you basically consider a cone, if you basically have a cone, let's say, and then what happens is you basically have a solid angle here, because if you consider a two-dimensional picture and if you consider the angle, this is nothing but theta, right. But then when we consider a cone, we are basically having a three-dimensional picture. So a three-dimensional picture, let's say we have got an ice cream cone. We have got an ice cream cone here, and then ice cream cone, the angle that it suspends, okay. So this is basically a two-dimensional image. But try to remember this or try to understand this from a three-dimensional picture in ice cream cone. We basically have this angle, which is nothing but the d omega angle. So this is something which is called the solid angle. A solid angle is a very important factor, and we need to understand this because the scattering that happens in nuclear physics is more or less going to be three-dimensional in nature. So ऐसे idealized case करके theta ले लिया means we are making our work easy, but we are not making it practical. So we have to consider a solid angle. Very important. Next, intensity of the projectile. Now intensity is also very important. You know that how many number of particles are getting incident per unit area per unit time. So if you know that, we actually know that how many particles are getting incident. So number of particles crossing the unit area in unit time. Okay, so this will actually form the factor. So if we basically have this much of area and then we have the particles getting incident on it, we know that more particles are there. But if you consider a lesser area, we know that less number of particles are getting incident. So that means this is very important. Okay, so please try to come in terms with these important notations. Okay, because this is something which you're going to use again and again, so I made it mandatory that you know this so that we can use it later. And then NT, number of target particles. Oh, I think this is also very simple. Of course, scattering will depend on how many particles are there at the target. So if you consider something like a gold nuclei or a gold foil, okay, you're going to have more number of targets, okay, more number of targets. But on the other hand, if you're considering something, let's say gas, okay, you're considering helium gas, or you are considering, let's say, hydrogen gas or deuterium gas, okay, you're just enclosing it within a box, okay, within a closed system, and then you are allowing the incident particle to come and get hit. So what happens is the number of particles getting scattered by gas would definitely be less compared to the number of particles getting scattered by a gold foil, okay, depending on the density. So that means number of target particle is important. Next, NA, aerial velocity. Now let me tell you, uh, this aerial velocity is important. Sorry, density, not velocity, density. Don't get confused here. It's not density, it's aerial density. So in general, when we write down density, we write it down as mass by volume. And I think mass by volume is a very simple idea. Okay, we already know it. But when we talk about aerial density, we are talking not about mass by volume, but mass by area. It's mass by area. Okay, so whenever we have density here, in this case, in scattering cases, it's mass by area. So please, number of particles by area. Okay, sorry, not mass, number of particles divided by area. So please don't make this mistake in exam of explaining aerial density as mass by volume. Don't do that. Okay, because aerial comes from area, and then of course A is the area. So these are some of the important terms that we should actually know, okay, for use in different formulas. Well, let's get into the formula now. So when we go into the formula, what is dn? Dn is the number of particles which is basically getting collected in the detector. So if you are going to study a system and you know that you are getting a wave which gets deflected from the target, and that wave is actually carried by that particular particle, you need to detect how many particles are going into the detector. Okay, and then you should know that on what factor these number of particles depend. Okay, very important. So what are the factors? The first factor is time. Now I think I have explained all these terms, we can easily understand this. Let me tell you, this is not something new for you, because when you studied Rutherford scattering, you actually came across these terms. Okay, but I just made sure that all of us still recall this. Okay, very important. So for how much time it is getting incident, that will be one factor. Of course, the solid angle, because as I said, three-dimensional picture, I intensity, and now we know intensity is nothing but number of particles. Okay, so why this is there all the time? Okay, so what is this intensity? Number of particles per unit area in unit time. Okay, and NT is the number of target particles. So let me just tell you this, okay, something which might be a bit scary for you, that this chapter on in nuclear physics can get a bit tricky. Okay, I can ask you a question and you might give an answer. You might be very confident you've answered it correctly, and then somehow you'll end up with a wrong answer. So please try to understand the concept, very important. So then we need to actually, it is proportional, so I need to include a constant here, and that constant is one of the terms which we come across again and again, that is sigma. Okay, we are using the nuclear cross section term, and this sigma has to do something with the cross section. So what happens is, if you are basically considering a particular system, let's say you are considering a gold foil and you have got alpha particle coming in, it has got a fixed sigma value. On the other hand, if you consider something like let's say a hydrogen atom, let's say deuterium, okay, and we have got a proton coming in, that constant will change. Okay, so that depends on that particular system that you are considering, of course. Okay, and then this is number of particles collected in the detector, and then we are replacing by constant, and everything else remains the same. Okay, so I'd like you to all concentrate on the screen and don't lose track of what I'm saying now. Okay, please don't lose track. This is T, this is d sigma, this d omega, sorry, this is I, this is nt. Now what is nt? Number of target particles. Okay, and then number of target particle will depend on the areal density and the area. I think this is quite obvious, because this is a number and areal density is number of particles per unit area, so it will be n. Okay, and then this is nothing but into area. So if you just multiply this, area gets cancelled, you again get back the number. But then whenever you want to know that how many particles exist within a system in general, we consider the density relation, right? We know how much is the mass per unit volume. So if something is very heavy, that means the density is more. That means there are more number of particles. If something is very light, density is less number of particles. And that's why we just don't write down n into t, we write down Na into A. Very important. Okay, so this is the areal density. So please replace this Nt by Na into A. And then the other term remains the same, d omega into I. Okay, so what happens is that we actually are going to get a relation now. Okay, we are slowly arriving or moving towards Rutherford scattering. Okay, so what happens is, this is the constant, this was the term, we have Na into A, which is nothing but Nt. I think simple. Now what is the number of projectile particle hitting the target? So look here. So when we talk about the number of projectile particle hitting the target, it depends on a number of factors. First factor, for how much time it is going. Second factor, what is the intensity of that projectile, and of course what is the cross sectional area. Okay, so on how much area it is going to get incident. Okay, and then with what intensity is getting incident, and of course what is the time for which it is getting incident on the system. So if you consider all, what you're going to get is a single term NP, and this is nothing but the number of projectile particle hitting the target. Okay, try to think about it logically. Okay, I might explain it 100 times, but still you might not find it convincing enough, but try to understand it logically and you'll think that yes, this is correct. Okay, so what happens is, we can just replace this T, I and A with NP, and what we are left out here is with nothing but T omega and Na. So this is a simplified equation which has got all the parameters involved. So if someone asks you a trick question, that imagine a cross-sectional area and then we have got a intensity of a beam of, let's say, this much lumen. Okay, and then this is incident for, let's say, 2 seconds. What are the number of particles hitting the target? Okay, so might be a trick question. You can always answer that using this formula, and this is not very common. We don't come across these formulas again and again, day in day out. So please try to concentrate on this. Okay, and then we can just put sigma on one side and then the remaining part on the other side. So we have got this Dn already explained. Okay, and then d omega Na NP. This term is called the differential scattering cross section. This was actually experimentally determined also for different systems. Okay, so if we just look into the units, you don't need to get confused, because Dn is a number, no unit. Omega is angle in radians. Okay, no need to consider that. Np is again a number. Okay, if you do this, you will find out that this is also just a number. Okay, just a number. Only remains Na. So what is this Na? So Na, we know it is nothing but number by area. Okay, Na is here, areal density, number by area. So number by area, again a number. This area can go up. This is centimeter square. So when we say centimeter square, that means we are talking about area. When it is area, we are talking about sigma. Sigma is scattering cross section. Okay, scattering cross section, very important. So we come across these terms and there are different names given to it. Okay, so this is very important. So I think we should not proceed further, because if I go next slide I think I have to take more time. Okay.